The salt ring is still holding for our victims, folks, as we learn more about delta G naught. This time using another way to calculate delta G naught of the reaction by applying Hess's law. Using Hess's law, we now get a chance to use the standard free energy of formation values, similar to the standard enthalpy of formation values that we get for delta H naught of the reaction, right? So delta G naught of formation is the free energy change when 1 mole of a compound forms from its elements in its standard state. So when I always say, oh, delta G naught can be kilojoules or kilojoules per mole, it's because we are using standard values for our variable. Before it was delta H naught and delta S naught. This time is going to be delta G naught. So applying Hess's law, we're going to combine delta G naught of formation values for reactants and products. And this is going to be irrespective of the reaction's conditions. So we can say delta G naught of the reaction is equal to the sum of the products or the moles of the products multiplied by their delta G naught of formation value. We're going to subtract that by the sum of the moles of the reactants multiplied by their delta G naught of formation value. If these values are given to you, you have the ability to complete this overall expression and solve for delta G naught of the reaction without enthalpy or entropy being involved. So when we talk about delta G naught of formation, we're talking about the same type of standard values as we saw with delta H naught of formation. The properties are elements in their standard state are going to be 0, which we see here. We have carbon, graphite, which is 0. We have Br2, which is its standard state, is going to be 0 here. Into gas, its standard state is going to be 0. Also, the number of moles for reactions or products are going to be multiplied by delta G naught of formation, exactly like we saw with enthalpy. Here we see the number of moles of a product, number of moles of reactants, all multiplied by their delta G naught of formation value. And then finally, if you reverse a reaction, you have to change the sign of delta G naught of formation. So initially, if you were given a negative delta G naught of formation sign and you have to reverse the reaction, your now delta G naught of formation sign will be positive. Here is just simply a table of selected standard free energies of formations at 298 Kelvin. So we have bromine, calcium, of course, everything's in a different standard or physical states as well. And so change your physical state, you're going to change your delta G naught of formation value. So that's just a little table that you can use. Let's use what we know here as a weapon to continue to help temporarily. To Dad's car we go for an example, folks. All right, we are back at Dad's car and we want to use what we know as a weapon to help against this entity. This question says, calculate delta G naught of the reaction from delta G naught of formation value. So you're going to use delta G naught of formation values to calculate delta G naught of the reaction for this reaction here. 4 KClO3 solid to form 3 KClO4 solid plus KCl solid. Oh, what happened here? We are seeing the exact reaction as we saw before. So what we're basically verifying is that us calculating delta G naught of the reaction is going to be the same no matter if we use delta G naught of formation values or if we use standard enthalpy, temperature, and standard entropy values. So let's get to it, folks. The first thing we need to do is write our expression for our delta G naught of the reaction. All right, delta G naught of the reaction is going to equal to the sum of the moles of the products multiplied by their delta G naught of formation value minus the sum of the moles of the reactants multiplied by their delta G naught of formation value. So since I already have my products here and my reactants, I go ahead and plug it in. I get 3 times negative 303.2 kilojoules per mole. Now again, these delta G naught of formation values will be given to you, most likely in a table in any type of question on an exam, for example. Okay, so when I multiply this number here, I get negative 909.6. I'm going to add that to 1 because we have 1 for KCl here, multiplied by negative 409.2 kilojoules per mole. So I just have a negative 409.2 kilojoules per mole here. I'm going to add these two numbers together, and I get negative 1,318.8 kilojoules per mole. Now let's focus on summing our reactants. We only have 1 reactant here, so I just got to get my delta G naught of formation value for KClO3. I'm going to take 4 multiplied by negative 296.3 kilojoules per mole. I get negative 1185.2 kilojoules per mole as my value. Now, in order to solve for delta G naught of the reaction, I'm going to subtract these two numbers. Negative 1318.8 minus negative 1185.2. I get negative 133.6 kilojoules per mole, folks. And again, this is just another way to calculate delta G naught of the reaction. In our previous example, we got negative 133.2 kilojoules per mole. You see how close that is? Because they're so close, this is why there's multiple ways to calculate that delta G naught of the reaction. So if you're given delta G naught formation values, you can calculate it that way. Or if you're given your delta H naught minus your temperature delta S naught, you can also calculate delta G naught of the reaction that way. Using this new weapon of information, the ghost continues to remain settled, folks. Let's continue.